Building a research agent means building a loop, writing the tools it can call, choosing how it decides what to do next, specifying what it must return, and anticipating how it breaks. Building that loop yourself, rather than configuring a pre-built one, is how you learn exactly what the agent can and cannot do, and where to intervene when it fails. This assumes you are comfortable operating an agentic rig and directing an agent to write code, one framing before the mechanics. A system can sit anywhere on a spectrum. At one end, an agent, the model chooses each action at runtime. At the other, a workflow, the steps are fixed in code. This video builds the agent end deliberately, not because it is always right, but because it is the newer, less familiar capability, and we return, at the end, to choosing where each system belongs. Here is the ground we cover. What a tool is, the React loop, structured outputs, ways the loop can fail, and the build you should actually choose. Start with the tool. In the context of building agents, a tool is defined by three things: a name, a natural language description, and a parameter schema. The model reads all three when it decides which tool to call and how to call it, which makes a tool definition as much a piece of documentation as a programmatic contract. Of the three, the description is the most consequential. It tells the model when to call the tool, what the tool expects of each parameter, and what the tool returns, so the model knows what to do with the result. A vague description produces inconsistent tool use. A precise one produces reliable behavior. This is a genuine departure from how software has classically been built. A traditional function is called by code that already knows its exact signature. The contract is rigid and the caller's behavior is fixed. An agentic tool is invoked instead by a model that reads its description and decides, by interpretation, whether and how to call it. The description is closer to a specification in plain language than to a type signature. That latitude is the source of the power. One clear description lets the model handle inputs and situations the author never enumerated. It also carries a cost. Interpretation can go wrong where a fixed call site could not. And an agent that chooses its own tool use tends to enlarge its own footprint. The more freedom it has, the more it presumes broad access to files, commands, and the network. This is why a toolset is a security surface as much as a capability, and why least privilege is a discipline worth keeping. Concretely, here is a tool schema in the shape the Anthropic API expects. A name, fit model. A description, in plain English, fit a candidate symbolic expression to the training data and return the mean squared error on the held-out validation split. Then an input schema, one required parameter, expression, a string, with its own short description and an example. Look at where the weight sits. The name and the schema are a few tokens each. The description is where you tell the model when the tool applies, what the expression must look like, and what comes back. Spend your effort there. A precise description is the difference between a tool the model calls reliably and one it calls inconsistently or not at all. Several principles guide a useful tool set. One tool, one responsibility. A tool that both fits a model and plots the residuals is harder to invoke correctly than two separate tools. Smaller, focused tools compose more reliably. 2. Be explicit about side effects. A tool that writes a file, posts to an API, or spends tokens should say so in its description, so you can decide whether the agent may call it without approval. 3. Return only what the model needs. A tool that returns 100 lines of raw data when the model needs a single score fills the context window for nothing. Post-process to the informative essentials. 4. Return informative errors. When a tool fails, its error message becomes the model's next observation. An error that says shapes 30 and 40 are not aligned lets the model self-correct. An error that just says error does not. Notice what those 4 principles are. Single responsibility, error handling, minimal interfaces. They are classical software engineering discipline reappearing at the tool boundary. And that's worth pausing on because it is a pattern that runs through all of this work. Agentic coding contracts out the typing. The agent writes the implementation behind each tool, but it does not contract out the understanding. To specify a tool well and to tell a sound one from a subtly broken one, you still reason about data structures, execution order, and how errors arise and propagate. The mechanical compresses. The conceptual endures. The time spent writing code shrinks. The need to understand computing does not. Here is a tool call in practice. Turn 1. The model proposes a candidate and calls fit model with the expression x0 squared plus x1. Turn 2. The loop runs the function, collects the result, and appends it to the context as a tool result message. Mean squared error 0.0023. Turn 3. The model reads that result alongside everything before it and decides what to do next. Try another expression or produce a final answer. Each result is an observation, and the model acts on it. A single turn need not carry a single call. When a task fans out into independent subtasks, fitting 5 candidate expressions, querying 3 data sources, a frontier model can emit several tool calls at once. The loop runs them concurrently, appends all the results as a batch, and reinvokes the model once. The round trips collapse from 1 per call to 1 per batch, and the model reasons over the whole set together. When the reasoning between actions is made explicit, the loop has a name, REACT, for reasoning plus acting. The model writes a thought, natural language reasoning about what to do next. Then an action, a tool call. The tool result comes back as an observation, which feeds the next thought and the next action, and the loop continues, exiting only when the model produces a final answer instead of another tool call. The explicit thought step does 2 things. It conditions each action on intermediate reasoning rather than jumping straight from context to action, and it leaves an audit trail. By reading the thoughts, you can understand exactly why the agent made each call. The REACT pattern writes the thought into the transcript. Some frontier reasoning models move that step inward. They reason internally before emitting a tool call, so the thought becomes latent rather than a visible entry. This is chain of thought reasoning, the model thinking step by step, now performed on its own rather than elicited by a think step-by-step instruction. A practical consequence: handwriting a thought and action scaffold buys little when the model already deliberates before acting. The liver shifts from a prompt template to a thinking budget, a cap on how many reasoning tokens the model may spend before it must answer. The cost falls on the audit trail. When reasoning was a transcript entry, you could read why each tool was called. When it is latent, that record is gone, and even where the internal reasoning is surfaced, it is not necessarily a faithful account of the model's computation. So the dependable audit trail is the observable one, the sequence of tool calls and their results, which the loop logs no matter what the model reasoned inside. Now, what the agent returns. An agent that produces unstructured text is an endpoint. An agent that produces structured output is a component, one whose result can feed the input of the next without brittle string parsing. The final output should conform to a schema known in advance. In Python, a pydantic model expresses it cleanly. A model result with an expression, its mean squared error, a complexity, a composite score, and a 1-paragraph justification, each with a declared type. 2 mechanisms enforce it. The stronger one: give the model a tool, submit result, whose input schema is exactly the output schema. To answer, the model must call that tool with correctly typed arguments, and the tool calling layer guides it toward valid ones. The weaker one: instruct the model to produce JSON, then parse and validate, returning the error and reprompting on any mismatch. Prefer the first, where the API supports it. But in both cases, the calling code remains the authoritative validator. Agents fail. Knowing how they fail lets you design loops that catch it early. 4 modes recur. 1. Hallucinated arguments. The model calls a tool with a plausible but wrong argument, a column that does not exist, a function from a library that is not installed. Good descriptions and schemas that constrain a parameter to a fixed set of choices reduce these. 2. Loops without progress. The model calls a tool, gets an error, tries to fix it, gets the same error, and repeats. The loop needs a maximum step count, exceed it without a final answer, and exit and report. 3. Context overrun. The window fills before the agent finishes, usually from long tool results, stack traces, raw dumps. Truncating tool results to their essentials is the main defense. 4. Cascading errors. A mistake in an early step propagates silently. Fit on the wrong data, score that data, select it as best, and the score is meaningless. Validate at each tool boundary, check for known failure conditions, and inspect intermediate outputs, not just the final one. When a run misbehaves, the diagnostic unit is the trace, the logged sequence of tool call, arguments, observation. Walking it localizes the fault, not the final output. Step back to the spectrum from the opening. Everything so far, tools, the React loop, structured outputs, built the agent end, where the model chooses each action at runtime. The other end is a plain program, the steps settled in advance, no model deciding anything as it runs. The point worth drawing out is that agentic development builds both. The skill is the same, only the target moves along the spectrum, and there is real value in aiming deliberately at the fixed code end. A workflow is deterministic, cheap, fast, and auditable, and it is robust to model evolution. A fixed program does not change when the underlying model is updated, retired, or repriced. For a pipeline, a lab expects to rerun for years. That stability is not a minor convenience. So the principle, fix in code what is stable. Reserve agents for what must adapt. Reach for the workflow end when a task is well understood, repetitive, and expected to recur. Reserve full model-guided execution for the genuinely open-ended. The strongest designs are often hybrids, an agent composing deterministic components with proven agentic procedures graduating into workflows over time. One more knob cuts across the whole spectrum: how much computation to spend at inference. The same model, given a larger thinking budget, can solve harder problems, so capability can be bought at runtime, not only by training a bigger model. It sharpens the case for an agent on open-ended work, where spending more thinking pays, and it raises a running cost that a fixed program, calling no model, sidesteps entirely. Here is the agent loop on one card. The tool, a name, a description, a schema, and the description is what the model reads. The loop, thought, action, observation, until a final answer. The structure, a schema the calling code enforces. The failure modes, hallucinated arguments, stuck loops, context overrun, cascading errors, all read from the trace. The choice, workflow or agent, fixed where stable, adaptive where it must be. And the key idea to carry away. You build the loop and you choose where on the spectrum it belongs. The model can write the implementation and drive the execution, but specifying the tools, enforcing the structure, and reading the trace stay with you. The mechanical compresses, the conceptual endures.